In this lesson, we're going to continue on with Unit 4, Acquisition 3. We're talking about polarity still. Last lecture, we really focused on bond polarity. How does the difference in electronegativity affect whether we have polar bonds or nonpolar bonds? What we are going to focus on today is called molecular or overall polarity. Is the overall molecule polar or nonpolar? When we're doing molecular polarity, it depends on the sum of all the individual bond polarities. I'm going to bring us back to physics. Think in terms of vectors. And remember that vectors deal with both magnitude and direction. Magnitude is going to be the difference in electronegativity. Direction we'll look at in just a second. All right, first one we're going to do. Carbon dioxide. Let's do bond polarity and molecular polarity. Predict the bond polarity and overall polarity. And first one we said we're going to do is carbon dioxide. So I'm not going to go through the steps on how to draw the Lewis structure for carbon dioxide. We spent a lot of time working on Lewis structures. Carbon dioxide should look like this. We have two double bonded oxygens, and it is linear. If we were to do our Vesper geometry, it is linear. Let's start with bond polarity. Bond polarity depends on the difference in electronegativity. So I want to use my Honors Chemistry resource packet. Oxygen 3.44, carbon 2.55. Always do the bigger number minus the smaller number, and my difference is 0.89. I could use the table at the bottom of my reference sheet. 0.89 is a big enough difference in electronegativity that this would be considered a polar bond. So that's the first part of this question. The bond polarity is polar. When we are looking at overall polarity or molecular polarity, we need to look at the entire molecule. Here's where vectors come into play. Oxygen has an electronegativity of 3.44. Each oxygen has an electronegativity of 3.44, and carbon is 2.55. Remember, electronegativity is the tendency to attract electrons. Oxygen is more electronegative, so it is going to pull the electrons closer to it. But this oxygen is also more electronegative, and it is going to pull the electrons closer to it. Think about vectors. Think about your physics class. Vectors have both magnitude and direction. The difference is going to be the same. But they're going in opposite directions. That means the vectors are going to cancel. Same magnitude but opposite direction means those vectors will cancel. That means this is a non-polar molecule. It is not polar because I'm not going to have any poles. The electrons are being pulled equal but opposite, which means they cancel. This diagram is showing an electron density graph. This is from our Pearson textbook for Master in Chemistry, section 9.3. So here is carbon dioxide, and again we have carbon in the middle and we have the oxygens on the outside. These numbers represent our electronegativity values, they're just rounded. So again, we can see that the vectors are equal but opposite. That means the overall dipole moment is 0. We are not creating dipoles. Since there is no dipole, it is overall nonpolar. B. Let's do the same thing with water. Again, I'm not going to go through how to draw the Lewis structure, but one thing that I will say, when you draw your Lewis structures, you need to take VSEPR into account. We need that molecular geometry. It's going to make things so much easier. So this is what my Lewis structure of water will look like, and water has a bent shape. So I'm showing that it is bent. Let's start with bond polarity. Oxygen is 3.44. So then I can grab my reference sheet and I could look up hydrogen. Hydrogen is 2.10. So my difference would be what, 1.34. So first we'll start with bond polarity. 1.34 falls in the range of having a polar bond. Its bond polarity is polar. But that doesn't mean that it's a polar molecule. We saw with carbon dioxide, you can have polar bonds with a non-polar molecule. So now let's draw in our vectors. Electronegativity is the tendency to attract electrons. Oxygen is more electronegative. So the electrons are going to get pulled closer to oxygen. Pretend I drew my arrows better. They're going to be equal in magnitude. But now, what would the overall vector look like? If you were to add these two vectors together, are they going to cancel? No. We are going to have an overall vector pointing up. That means that we are creating two separate poles. If the vectors do not cancel, if we add our vectors, this would be a polar molecule. We are creating poles. So again, let's go back to our Pearson text from Master in Chemistry and look at the example on the right. So this represents water. Again, oxygen is more electronegative, so it pulls those electrons closer to it. We are going to have an overall dipole moment if we add those vectors up, pulling forward. If we look at our electron density diagram for oxygen, I have that high electron density area. This is going to be my negative pole. I have a low electron density area. That would be my positive pole. It has two poles. It produces a dipole. So this molecule is polar. Let's look at a few more examples. C. Let's do HCN. Alright, so I'm going to start by drawing the Lewis structure. Again, you guys should be able to draw the Lewis structures. We spent a lot of time working on them. My Lewis structure would look like this. Triple bond between that carbon and nitrogen. Alright, so we have two different bonds that we can figure out if they are polar or nonpolar. So I have a bond between carbon and hydrogen. Carbon is 2.55. Hydrogen 2.10. So that gives me a difference of 0.45. I also have bonds between carbon and nitrogen. So what if I wanted to know, is this bond polar or nonpolar? Nitrogen is 3.04, and again, I'm just getting these numbers from our resource packet. Carbon is 2.55. If this were a test or quiz, it would be very specific. I would say, is the bond between carbon and hydrogen polar or nonpolar? And then you can calculate that one. So you will definitely know which bond is being asked. Both of those values fall below 0.5. These are going to be nonpolar bonds. That's the first part of this question. Remember, we're predicting bond polarity and molecular polarity. When we're thinking about molecular or overall polarity, think in terms of vectors. Carbon is more electronegative than hydrogen. So carbon is going to pull those electrons closer to it. Let's compare nitrogen and carbon. Nitrogen is more electronegative. Again, pretend my arrows were to scale. Vectors have magnitude as well as direction. Do these vectors add or do they cancel? Well, they're both pointing this way, so I'm going to have an overall dipole pointing this way. The vectors add. That is going to create a dipole. It's going to create a separation of charge. All the electrons are getting pulled this way, making this end more negative. It's inducing that pull. I'm going to have a negative pole and a positive pole. If your vectors add, or if they do not cancel, this is a polar molecule. So here's another example. It's not always the same. You can have nonpolar bonds on a polar molecule. You can have polar bonds on a nonpolar molecule. They may both be polar. They're not always the same. So it's really important that you go through and see, calculate the difference in electronegativity, and then look at those vectors and decide, is it going to be polar or nonpolar? Let's do one more. Let's do methane, which is CH4. This one's a nice, easy Lewis structure to draw. We've already done bond polarity, so I'm not going to go through that again. Bigger number minus smaller number, let's do carbon minus hydrogen. We get a difference of 0.45. My bonds between carbon and hydrogen are going to be nonpolar. Let's look at our vectors. Carbon is more electronegative than hydrogen. So it pulls those electrons a little bit closer, not very much. But look what happens here. This carbon is also more electronegative than this carbon, so it's going to pull the electrons closer. What happens if I have two vectors that are equal in magnitude but opposite in sign? These two vectors are going to cancel out. Well, same thing with my other two hydrogens. My vectors are going to point towards carbon. They're equal in magnitude but opposite in sign. That means these ones are going to cancel out. All vectors cancel. That means we are not creating any poles. This is going to be a nonpolar molecule. So the last thing I want to show you again is another figure from our Pearson text on Mastering Chemistry. So all the way at the left, fluorine is more electronegative than boron. So we see that our vectors are pointing towards fluorine. These numbers are my electronegativity values. But again, think about what this would look like if you were to add your vectors. All of those vectors would cancel. If the vectors cancel, it is nonpolar. Looking all the way to the right, carbon tetrachloride. This looks just like CH4 that we just did. Based on our vectors and our molecular geometry, all of my vectors are equal in magnitude but opposite in sign, meaning they are going to cancel. If your vectors cancel, it is nonpolar. It is really important that when we're doing this, we take VSEPR and molecular shape into account. So here I have NH3. Up here, it's not showing it, but we would have a lone pair of electrons, and that lone pair of electrons is going to push those three hydrogens down into this trigonal pyramid shape. So now if you look at your vectors, they are not going to cancel. We would have one vector pointing up when we add them together. If your vectors do not cancel, it means that it's polar. Last thing I want to touch on. Just because molecules are tetrahedral doesn't mean that they are always nonpolar. In the case of methane, CH4, and carbon tetrachloride, they are nonpolar. In order for them to be nonpolar, all of the attachments to the central atom have to be the same. If I look at this molecule, this chlorine makes it polar. These two vectors would cancel, but these two vectors would add. The electrons would be pulled closer to carbon, but then chlorine is going to pull those electrons closer to it. This chlorine makes it polar.